Can you hear me, Seth? Yo, Seth, I need you to unmute yourself. Seth, hello. Oh, man. You see, is he lagging or what? Seth, can you move your iPad to somewhere closer to the Wi-Fi or not? Yeah? Okay. So all the forces are the same. Which one gives you the largest moment? Right? How do you calculate moments? Moments is force times perpendicular distance from line of action to pivot. Right? So your job, you literally can go and take your ruler, okay, and go and draw all the perpendicular distances from all these forces here, and then you go and measure which one is the longest line. Okay, because I want you to learn how to find that perpendicular distance. Okay, wait like on your paper now, you legit go and draw this one. Do you see this? You see that this is the line of, this is the distance. The line of action of A is this line here. The distance is this distance here. Okay, let me zoom in a bit more. Sorry, let me zoom in a bit more. Let me move it there so. Right, this distance here. Okay, now how about D? How about D? So you realize that D, like very hard to draw a perpendicular, so you need to extend D. Right, do you see that? I'm extending D here like this, and then I go and draw the line of action to the pivot. This one, right? This will be DD, right? The red one will be DA. You see that? Okay, hang on. Let's do for C now. Let's do for C. Right. Again, right? I just draw the whole line of action for C like this. You see, I draw the whole blue line like this. This is C's entire line of action. Then I go and drop a perpendicular from the line of action to the pivot. Right? That's DC. Okay, that's DC. Okay? Now, I mean, maybe you got an idea what the answer is already, but I don't care. I'm just gonna draw B, for completion's sake. I'm gonna draw the one for B. Right? B, I use yellow here. Right? So you got a line. This is B's line of action. Right? And then you find the perpendicular distance to the pivot. Like B is the shortest. Look at that. B is the shortest distance. So the moments of B about this pivot is B times this. The moments of A is A times this distance. So if you do the measurement, I mean, from my point of view, I think it looks like A is the answer. A will give you the biggest moments, right? But why? Because A has the biggest perpendicular distance to the pivot. Okay, that's the answer, right? But I need you to see the others because I can switch this question around and ask you which one gives me the smallest moments. Right? Then you should understand that B gives you the smallest moments. Why? Because, like, when you draw the line of action of B, right? So the line of action is this entire line here, like this entire thing here, like that. Right? Then the distance here, like this. Okay? Okay. Hang on, Just to be fair with everyone's time, let me go through Garen's one, right? Because I know you got 3 questions here, but I'll just leave it here. I'll go to the next page. Right? Now I'll do round robin. Okay. Garen, what's your question here? Oh, okay. Firstly, what? Okay. Then the question is asking you, particle X, where is it going? Where is it moving? During the next half cycle and the wavelength of S1. Okay. Firstly, yeah. S1 is a lower pitch, right? No, sorry. S2 is a lower pitch. S1 is higher pitch. So based on V equals to F lambda, S2 will have a longer wavelength. So your options are either C or D now. Okay? Okay. This is actually a very difficult question. So to answer this, I will refer to the graph, a displacement distance graph. And I'll draw a graph like that. Can? Okay. Where is a compression particle? That's the thing. On this graph, remember, I know it's X. X is a compression particle, right? You see the particles are all going towards him, right? X is a compression particle. But where is it on this graph? Good. Very good. Right? The rest of you must also make sure you understand this. So X is here. Okay. Can you describe the speed of X to me now? What's the speed of X? Good. It's traveling the fastest. You're right. Okay, it's traveling the fastest. Where? That's a very common fallacy. That's a common mistake. Right? This is a snapshot picture. The snapshot picture is showing you that at one instance, this particle is actually passing through the equilibrium and it's the center of compression, but it's actually moving at a faster speed. Let me show you a GIF. Maybe it will help you, hopefully. And you can see that when the particle goes through the equilibrium, when it's the particles at the compression, it's actually traveling fastest. But you have to kind of like see it very carefully. I will try. If you cannot see it, then never mind. Right? We try again another time. But for now, I will just try to show it to you. Okay. See, Okay, you see this? Particle compression. Particle compression. Particle compression. You see? When it's at the center of a compression, it's actually traveling through its middle portion. Let me okay. Where's the I think the amplitude points are here and here. You see this, See my hands there, right? So the particle is moving in between my hands, right? And my hands keep. Correct. When it's in the center and the compression is going past it. You see that? Yeah. So it coincides. So when the compression coincides with its motion, the particle is at the center of its displacement. So which means that it's at equilibrium. It's passing through its equilibrium. Passing through equilibrium. Like that. Passing through equilibrium. Right? Then passing through equilibrium. That means maximum speed. Compression, maximum speed. Right? Compression, maximum speed. Compression, maximum speed. Like that. Okay? In fact, rarefaction as well. Rarefaction as well. Look at this, Rarefaction coming along, right? But particle moving backwards. So refraction, maximum speed backwards. Refraction, maximum speed backwards. Like that. You see that? So compression, refraction particles always travel at their maximum speed. All right, so down here like this, you see? This one here, right, is at maximum speed. So it's a very common mistake to say that it's at rest or it's at equilibrium. So therefore you think that's not moving, but it's actually maximum speed. But now I'm gonna ask you this. The wave is traveling towards the right. The wave is traveling towards the right. Okay, so you have to draw a shifted to the right wave like that. You see that? Wait, So you have to shift the wave to the right side like this. Right? So where is the particle going? It's going, I mean, on this graph, the particle will go up, correct? But for a longitudinal wave, the graph, the x, the up and down, this one here is actually the right and left. Right, left. So for in this instance, it's moving to the right. Now, the question is asking you, what's the movement of x during its next half cycle? That means half a period. Okay, half a period. Right, half a period. So how does half a period look like? So half a period will look like this. It goes, so basically it goes like, wait, let me just draw one line here first. Okay, I draw the line to show you where is it going, okay? Okay, so it goes up, 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 and then down, 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 down. You see that? One more time, Right, so the particle here, right, as I move this, as the wave travels, right, the particle goes up, 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 and then it goes down, 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 down. So based on the motion of the particle, it moves right and then it moves left, but it goes back to its original position. Yeah, so C is the answer. Yeah. Okay. The one that slopes up. This one. This is a refraction. Compression particle, right? The slope is down. Refraction particle, the slope is up. Okay? Okay, good. So yeah, just be aware of this. Yan Hao's turn, hang on. Yan Hao only got one question. Okay, hang on. Hey, this one here, this question a bit tricky. As in like this question here, you shouldn't be not knowing how to do this. Okay. You know, the image will be here. Yes. Do you see that these light rays are coming from a distant object? Light rays from infinity. Light ray from infinity will form an image at F on the focal plane. That was the last part of my note, my lesson on light lenses. Uh-huh. Did you memorize the 6 applications of lenses? What do you mean not yet? Tomorrow is what? Paper 1 or both papers? Then you did. There are no lens questions for paper 2. Walao, you lucky. Tomorrow confirm got lens. At least got 2. And both you need to memorize one. I show you one that happened today, earlier today, okay? I show you one question that happened earlier today. One of my year 4s. One of my year 4s give me this question. Oh, sorry, they took it from a paper and I forgot which paper it was really. Wait, let me see first. It was the CHIJ 2025. Hang on. Come, you try this one. Now. I tell you lens questions, right? All of them are all to be memorized one. There is no lens question that's not memorized. Right? Inside my lens video, right, I tell you that if you don't spend time memorizing it, you will not get any of your lens questions correct. This is one of them. What's the answer for this? Answer is D. In your 6 applications of lens diagrams, 5 of them, at least 4 of them, actually 5 lah, 4, forms an image on the screen. Okay? But anything to do with the screen on the other side of the lens is always an inverted and real image. There's only one use of the converging lens that gives you a virtual upright image, and that's when you use it as a magnifying glass. This is when your object is here and your image is behind here, right? And behind that, then you have to put your eye here. You have to look through the lens and look at the image. The image will be here, right? The screen here, right? The screen here, right? If they tell you that the image on the screen is definitely always inverted, because of all the 6 lens applications that we do, right? Whenever we use a screen to catch the image is always inverted. You have to memorize all 6 of them. It's not something that you can work out or understand. It's not about understanding. It's memorizing all the 6 applications. Inside my video, I did give like a shortcut way to how to memorize all 6 of them. Please go and make sure you memorize all 6 of them. Okay? Yeah. Okay. Back to this one. So this one's straightforward, right? Very first thing that happens is, right, that you know that if the image is coming from infinity, sorry, the light rays from the object is coming from infinity, it will definitely form an image, right, that's inverted, right, and real and diminished at the focal plane. That means you have to put your screen here to capture this image. All right. Okay. But you could have worked this one out. How to work it out? Luckily, this didn't come out for paper 2. But sooner or later will come out. You could have worked this out. What you're supposed to do is draw light rays that are parallel to these light rays and let it cut through the center first. Right? If you watch the lens video, I mentioned that every time you do light construction, you always draw the one that passes through the center of the lens because that light ray doesn't bend. Right? Why do I draw a parallel light ray? Because parallel light rays are all coming from a distant object. A distant object, light rays are parallel. Then I draw the next one that cuts through F. So very conveniently, they gave us the focal point on this side. So if you were to connect the two and continue drawing, you will realize that the image will be formed at B, right? Your picture is taken a bit skewed, right? But you will get an image at B here like this, okay? You could have worked this out because they are very kind to you. They gave you the diagram. You still could have drawn it out and realized that, oh, the image is at B. But I swear a lot of the other questions you need to memorize. Okay? Right, so please go and memorize your 6 lens diagrams. Let's get back to Seth. Hang on now. Oh, Seth's question is not done yet for this one. Okay. What is your question for 17? But, I mean, okay, good. So it's 5 times 70, right? Versus 20 times 12. Versus 20 times 12. And then you have to decide which one's bigger or which one's smaller, right? Which one's bigger, which one's smaller? Looks like the 5 times 70 will be bigger, I think. Right? Yeah. 350. That's 350, this one 240. Yeah. So the 350 will be bigger. So it will rotate clockwise. There will be a clockwise rotation. And there's only one answer that says clockwise rotation. So it'll be this, right? Okay, hang on. I want you to write this down. So net moments equals to 5 times 70 minus 20 times 12. Okay? So the very fact is that if you do get a net moment, 5 times 70 minus 20 times 12, you get 110 Newton cm, right? Or rather 1.1 Newton meter. Okay? So you got to understand that when your moments are not balanced, it will rotate. Rotational equilibrium means moments are balanced. So in this particular example, we're trying to show you, right? They're trying to show you that I'm giving you an example where the moments are not balanced, right? The clockwise moments is more than the anti-clockwise moments, and therefore you have to find what's the resultant moments. And you again must always remember it's always the perpendicular distance from the line of action to the pivot, So you have to repeat that statement in your head a few times because a lot of students they don't bother repeating it in the head, and therefore once they go to the exams they forget which distance are they supposed to use, right? Because in their minds it'll be like something 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 perpendicular something 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 like I don't know, like cannot remember. Then cannot remember, then you don't deserve the mark, no? Right? So please try to remember. Okay. Let's just finish this one up because I think you got quite a few questions also. What's your question here? What's this? So it says that it's a hollow cylindrical pipe. There's an inner radius and there's an outer radius. And the mass is 120 grams. Okay. So they tell you that aluminum is supposed to be 2.7 gram per cm cube. So your job is to understand that what if you had a solid piece of aluminum, right, of this external radius of 2 cm and the height of 15 cm, what would have been the total mass? Okay, then you take that total mass, you minus away the 120 grams, that will be the missing mass. Yeah, okay, then afterwards you find the volume. Okay, good. So that's for that. Wait, let's go back to Garen's question. Okay. Okay. Object placed 12 cm away from a lens, 12 cm. Okay. They say that linear magnification. Hey, wait, this is Garen, is it? Okay. So, Garen, you need to understand that there is an equation called m equals to v over u. V is image distance. Image distance. V is image distance. Image distance. You heard that? And U is object distance. Okay? So object distance is 12. Image distance will be 2 equals to V over 12. Right? So V will be 24. So, Oh, because they're asking for the distance between object and image, not between the lens. Yeah. So 12 plus 24. So the image is somewhere here, right? This is 24. So the total distance is 36. Good. Okay, Yen Hao, no question. Okay, we go through one more of Seth's. Okay, Seth, one more time. Okay. All right, so there we go. Of all the things that you didn't underline, see, it's significant. So the lighter ball will take longer to hit the ground. If there was no air resistance, D, both will hit the ground at the same time. But because when it's significant, then you have to see the bigger ball will hit the ground later. It will hit the ground with a greater speed. So air resistance significant for two different mass balls, right? It will look like this. VT graph. The more massive one will look like that. The less massive one will look like this. Okay. So this will be B and this one will be A, right? There you go. Right. In fact, B will land on the ground first, right? Okay, when these kind of questions, right, you extreme one, you just take it as golf ball versus tissue paper. You drop golf ball, tissue paper, which one will hit the ground first? Because that one air resistance very significant, right? Yeah. Okay, air resistance significant for that one. Okay, next one. Um, next one is Garen. Both questions, Garen? Okay. So train travels south and then okay, so don't care south, north or what lah, okay? It means traveling to one direction. This kind of south north is very annoying. So there's only two directions, south or north, okay? Fine. Okay, travel south at 35 along a straight track at time equals 3 seconds. Okay, right? Then the velocity starts to change and the acceleration is negative 2.5 meters per second squared. How is the train moving at time equals 16? Okay, so what it means is that you have a train that had an initial speed of 35 meters per second, right? But along the way, suddenly the acceleration, right, becomes. I mean, I already drew the arrow pointing to the left, right? So I'm just going to write 2.5 meters per second squared. Okay. So then what you can do is without using the Suvet equations, if you don't want to use the Suvet equations, you can kind of like just understand it part by part, right? Will the train come to a stop? Careful, The acceleration lasts for 16 seconds. This acceleration to the left lasts for 16 seconds. You think about this. Can you take 35 divided by 2.5? What do you get? 14. In 14 seconds, the train would have stopped. Right? And furthermore, after 14 seconds, the acceleration is still towards the left side. Because they are saying that this acceleration is being applied indiscriminately, is being applied to the left at negative 2.5 meters per second squared. It's not like, oh, once it stops, then no more acceleration. No. They stated that there's an acceleration here like this, constant. Which means that once the train stops, it will then start to go backwards. In 2 seconds, the last 2 seconds, it will be traveling towards the north, right? Towards the north, and the speed is still increasing because it's actually getting faster, right? Towards the north. So your answer will be B. Answer is B. Ah, shit. No, sorry, I forgot. The time equals 16 seconds. Sorry, it's 16 on top of the 3. Sorry. Ah, yeah. Okay, wait. Let me. So that means it's wait, this thing is damn annoying. So I forgot about the 3 seconds. So t equals to 3 seconds. For it to stop, it will be 3 plus 14, right? For it to stop, it will be 3 plus 14. It will be 17 seconds to stop, right? So at t equals to 16 seconds, hasn't stopped yet. So it's slowing down, traveling towards the south with decreasing speed. C is the answer. Sorry, I missed out the 3 seconds part. I thought it acted for 16. So it acted for another additional 13 seconds only. So not enough time for it to stop. But that means it hasn't stopped yet, it hasn't reversed yet. It's about to. That's right, yes. Okay?
Yeah.
Okay. This one also?
Yeah.
600 meters apart, accelerate from rest towards each other. Magnitudes of acceleration is 1 meter square. At what value do they meet? Okay. You can do this the graphical method, or you can do this via the equation method. Which one do you prefer?
Can you show both?
Can. Graphical method, you basically have VT for car A and B. This is car A, right? In certain time t, the velocity is 1t. Do you understand that part?
Yeah.
Okay. Then the distance traveled by car A is equal to half times 1t times t. Do you see that?
Wait, why is it 1T?
Yeah, okay. So you don't understand why is it 1t. V equals to u plus at, right? They start
Yeah.
from rest, so v equals to 0 plus at. The acceleration of a is 1, so v equals to 1t.
Oh, okay.
Right? No matter what the
Yeah.
t is, okay? So the distance traveled by a will be half times 1t times t. I mean, it's just t, but I leave it there. How about for B? B has a higher acceleration, okay? And dB, so dB equals what? Is 2t times t, right? So dB
Wait,
is
don't you get like half T square or something
for what? For
for dA?
yeah, sure. I mean, I'm leaving it there. I haven't calculated yet.
Okay.
Yeah. So the distance of B traveled will be half of 2t times t, correct?
Yeah.
And it turns out that when both of them, the distance add up, they meet at 600. right? I mean,
Yeah.
when the distance, they meet at a point between 600, so their total distance. So dA plus dB equals to 600. So half t squared plus t squared equals to 600.
Okay.
T equals, oh, actually, there's only this method. Sorry. The other method is the same thing. S equals to ut plus half at squared. You get the same thing.
Wait, is that a Suva equation?
Yes, it is. Do you use it? Do they
Uh,
teach that to you?
they taught it lah, but I don't really use it.
Yeah, I mean,
I
if you
just,
use a graphical
I
method, you don't have to use it.
yeah.
But I can show it to you. So SA equals to 0 plus half 1 t squared. SB equals to 0 plus half 2 t squared, right?
Yeah.
Yeah, it's the same more.
Then you just like equate it again to
Yeah,
600.
SA plus SB is 600. Yeah, that's right.
Okay.
Yeah. Okay. Wow, quite an annoying question actually. Back to Seth. Back to Seth. Seth.
Yeah.
Okay.
Wait. Yeah. Questions.
What? One more. One more. You have one more. This one.
Okay.
Okay.
Oh yeah. Okay.
This one here. Inertia is just mass. Inertia is just mass. Don't care where. Don't care what gravity. Don't care in outer space or not. The more massive it is, the more inertia it has. D is your answer straight away.
Yeah, I figured.
Yeah. Okay. Can ah? Okay. Not about weight It's
Yeah.
mass. Okay. Let's wrap it up with Garen. Garen got 2 more questions, right?
3, I think.
3.
Yeah, because the last picture has 2 questions as well.
Oh, no. Oh, the last picture has 2 questions. Okay, that's fine.
Yeah.
No worries. This one here. Bloody hell. Oh. Wait, Okay. Seth and Yen, how can you close your eyes, please? Because you don't need this. Okay, lah, but maybe it'll be quite interesting also. Lah. Okay. No, I actually.
Yeah. Mm-hmm.
That we may have to concern ourselves with.
Like work done.
Work done by what?
Uh,
Work done by an applied force. Okay?
yeah.
Is there an applied force on the box here?
Yeah.
It's by the rope, right?
Yeah.
Okay. Hang on. Okay. Then you have to concern yourself with work done by friction. Is there work done by friction here?
No.
Smooth inclined plane, no friction. Okay? Then we have to concern ourselves with change in KE. Is there change in KE here?
No.
Why not?
Because it's constant speed.
Constant speed. No need to care about change in KE. Then we have to concern ourselves with, okay, change in GPE. Is there change in GPE here?
Yes.
But if you want to find change in GPE, you need to know what's this height.
Yeah.
Okay, we'll leave it there. But so there is a 5th one, but it's not very common, and that is if they ask you for elastic potential energy. But then you will need a spring or some elastic rope, so this is not of our concern here as well.
Wait, do
So-
we have to know a formula for that?
Don't need. Half kx squared, have you heard of it?
No.
Okay, then don't need. Okay, but my point to you is this. After you've gone through this list, you realize that you only need to concern yourself with work done by applied force and the gain in GPE. Whatever the motor is doing is helping this box gain GPE. And GPE is mgh. The problem is you don't have the h. Instead, you have a triangle and you have the slope velocity of 0.43.
Yeah.
Okay? Let me help all of you, all three of you, to deal with these kind of questions. If you get this kind of questions where it's always like per second or like, you know, some rate or something like that, right? Or time or rate or anything, right? Or power, I want you to always quote this in your head. For every second, right? In 1 second, okay? In 1 second, how far does the box move up by? In 1 second, how far?
0.43.
0.43. In the same 1 second, how much height does it gain?
Then you do the trigo thing. Oh,
0.43 times sine 23.
yeah.
0.43 sine 23 degrees. Okay? Right. Work this
Yeah.
out. Can you tell me the value first?
Zero 0.168.
0.168 meters. In 1 second, the box will raise its height by 0.168 meters.
Yeah.
What this means is that the box will gain a GPE of mgh every second. And the GPE is coming straight out from the work done by the motor, which means that's the answer already. Because every second for the GPE gains, that's the power output of the motor. So power output of the motor is equals to GPE over 1 second per second, because joules per second gives you power. So M is 1.1 kg, G is 9.81 for you, H is 0.168 over 1 second. And what is this power?
1.81.
1.812888. This is your answer, C.
Oh, wait. Wait, but let's say, right, like, you calculate the GPA at the highest point, like H. Then you
Can?
divide it by, the 1.6 divided by 0.43.
Can?
You will get the same answer.
You will definitely get the same answer. So what you would want, like for your method, what you would have done is you have found the total height gained by the box. You find the total height, and that means the total GPE gain, and you went to find the total time it took for the box to go up there. Total GPE gain divided by total time taken, that will give you the average power.
How
It's the
about
same.
the power from the work done by applied force? Is the work done from the applied force used to change the GPA, so that's why it's the same.
Correct. The work done by the applied force is the work done by the motor. The motor is applying this force.
Oh.
Hang on, let me give you another example. So do a bit of side quest now, right? I give you a separate example. I give you a box, right, that's being slid up the slope with an initial speed of 20 meters per second, right? The box is 5 kg. And my question to you is, how high can it go? Right? And again, this is a smooth slope. I mean, just to make it easy. It's a smooth slope. How high can it go? So is there work done by applied force here? Is there any applied force here?
No.
Don't have. Is there any friction here?
No.
So what's going to happen to this box? When it goes up to the maximum height, what's the KE up there?
The MGH.
What's a KE? How much KE does it have?
Or like half mv square.
How much KE does it have when it reaches the maximum height? 0.
Was it because it's like wait.
What do you understand about the box going up to the maximum height? That means that that's the highest it can go, which means that the speed is 0.
Oh.
I'm not
Alright.
asking you what happens when it reaches the top. I'm asking you what happens when it reaches the maximum height that it can reach. Maybe it'll reach here, maybe it'll reach here, I don't know.
Oh,
You understand?
yeah.
Okay, so what happens to the energy? What energy is converted to what energy?
Ke to GPE.
So for this case here, it's half mv squared, right, equals to mgh, right? Then you can find h from it. So you're converting ke into GPE. Do we understand this?
Yeah.
Okay, hang on, stop. One more scenario. Right, I hope the rest of you are also paying attention. This one is also pertaining to you. Okay, I have a 3 kg ball, right? Right now the speed is 5 meters per second. Okay, right now the speed is 5 meters per second. It will fall for another 40 meters. Okay, it will fall for another 40 meters, right? So I tell you that it falls for another 40. Sorry. Right, it falls for another 40 meters. Then I ask you, what is the speed of the ball here? Right? So the idea here is the ball is losing GPE. As it loses GPE, it will gain KE, correct?
Yeah.
Okay, so what some students may accidentally do for this kind of question, and I swear, I hope you all don't make this mistake. All right, some students will do this. Oh, GPE convert to KE. Okay, then I take MGH equals to half MV squared because Sam said just now can show, right? So M3 times, I'm going to use 10, Garen, times H is 40, then half times 3 times V squared, right? So some students do this, right? What does this work out to? Don't do it because this is wrong. I'll do it for you. 3 times 10 times 40, then divided by 0.5 times 3, then square root of that bugger, right? So it's 28.3 meters per second. Then some students will then say that, oh, then I take this 28.3 meters per second, I add it to the 5, then they say there's a final velocity, right? So they say that, oh, the V final is 28.3 plus 5, right? Do you all see this?
Yeah.
Everyone, all three of you see this working here?
Yeah.
Right, he convert GPE into KE, right? Okay, then he went to find the speed, then he go add the speed, right? This is completely wrong. Do not ever do this. Right? That's like a sin, right? No way, don't do that. What you need to do is, okay, this is the initial KE. KE initial. This is the GPE. Okay? So what happens is that the initial KE plus the GPE will give you the final KE. So you have half mu squared plus the GPE change to KE, right? So plus the GPE mgh equals to the final KE half mv squared. All right. So take note of that. That it has to be done this way. Then you find the V, right? It is very, very different from doing this. This is completely wrong, right? You have to do it this way. So when you notice that there's initial KE and that there's final KE, right? Please, please, please remember this phrase: half mv squared, half mu squared. Oh, half mu squared, half mv squared. Right? Why? Why do I want you all to write this? What does half mu squared stand for? This is initial KE. Why? Because U is initial speed. Half mv squared. What does this stand for? This is final KE. Why is this final KE? Because V is final speed. All right, then you define it like that. I don't know what that one works out to, but I'm pretty sure you know what to do with that. Okay, back to your original question. Sorry. Yeah. So are we done here?
Yeah.
You got this one here? Okay, good. Let me do the last one then. Wait, last page. Actually, you know what? On that note, let me do one question from the The year fours. Because the year fours are also having their MCQ paper tomorrow. The ACSi year 4 IP. Okay, down here. Trolley runs from position P to position Q along a track. Position Q, the GPE is 55 kilojoules less than P. At position P, the KE is 5 kilojoules. Between the points P and Q, the trolley does 8 kilojoules of work against friction. So there's friction. What's the kinetic store of the trolley at position Q? Right? This question here is a little bit straightforward. Right? All you have to do is just energy accounting. Okay? Energy accounting. So, but some students are stuck on this because they keep thinking like the teacher say that, oh, total energy must be constant. Total energy must be constant. Okay? But then the teacher forget to say that total energy of the entire system must be constant. If you lose energy to friction, 8 kilojoules to friction, your 8 kilojoules is dissipated to surroundings. Total energy is conserved, yes, but the whole thing. But the trolley obviously doesn't conserve its energy, right? It only conserves energy when there's no work done against friction. Okay? So that's why sometimes whenever I hear the teacher teach like things like, oh, must be total energy, must be constant, I get very annoyed because it confuses the heck out of them. So, right, down here, the idea here is P, right, at position P has 5 kilojoules of kinetic energy, so 5 kilojoules of KE, right? I'm just going to write 5 kilojoules. And then on top of that, it actually has 55 kilojoules more GPE than P. So you know what? I'm going to write plus 55. Plus 55 kilojoules of GPE. Then this thing slides. And then it goes over to here. So by the time it reaches here, I'll tell you this. The 55 kilojoules will convert into KE also. Right? It will convert to KE. But it will lose 8 kilojoules along the way. So the final KE here is 5 plus 55 minus 8. That's it. 5 plus 55 minus 8. 5 plus 55 minus 8. Right? And that's 52 kilojoules. 52 kilojoules of energy there. Right? Because there's work done. Right? So the question didn't ask for final speed. Right? But if you had to find final speed, please remember, right? Take the initial KE first. And then find the final KE, then you go and find the final speed. Do not add speeds, add energies. Add and minus energy, then you find the speed at the very last step. Okay, sorry, this one here, I need to screenshot this one for him, right? I mean, if he doesn't understand, I will have to send him the recording now, because I'm just now going through this with you. Okay. All right, and then the last question for Garen. Okay. You're asked to find maximum efficiency. Garen, come tell me what's efficiency.
Like the amount that you calculated over what you're supposed to get times 100.
No. I mentioned this before many times already. Please try to remember it. Useful output over total input. Okay? So for the car, what is a useful output? It is a KE. There's no GPE, right? And if you do work against friction, it's wasted as heat. So the only useful energy is the KE gain. Okay? So we have to figure this out, right? So what is the KE gain by the car at the end of this final speed here? What's the KE gain? Half 850 times 14 squared. 14 squared, half mv squared. So how much is that? Please work it out for me.
$83300.
83300 joules. Okay, 83,300 joules. All right. This question is a little bit harder because now they want you to find maximum efficiency. I already found the useful output. That's the KE. The problem is the total input. Now the total input includes the KE that you have to add in. That's the input of the energy, right? Like how much energy does a car need to use, right, to give you the KE, which is obviously the amount itself at the bottom. But also at the same time, the bottom includes the energy used to overcome frictional force. Okay? Right. So you will have 83300 over 83300 plus, right, work done against friction, which is friction times distance. Now they give us friction, 120 newtons. That's great. That's great. But I don't have distance. I don't have distance. So you need to see for yourself that you can actually find distance. They give you the final speed. It tells you that it starts from rest and it's accelerating for 30 seconds, which means that the graph will look like this. The VT graph, right, will look like that. Right, this is 30 seconds. Maximum speed is 14. Right, so the distance traveled is,
The area under.
which is 7 times 30, 210 meters. Okay? So
Yeah.
the input the car has to do includes the KE that's gained already, and then you do work against friction, which is wasted as heat. So 120 times 210 for this one. Add this one, there's a denominator. Then this is your efficiency. What do you get for this?
Uh, 0.77. So 0.7677.
0. What? Sorry, what? 0. What?
0.7677. But
Okay
then like
lah.
it's in
So
percent,
C
yeah,
lah.
so it's correct.
C.
Yeah.
Okay, can. Okay, let's look at the last one here. What of the following physical quantities can be read off from the displacement time graph? Displacement time graph. Hey. Right? Displacement time graph. So displacement time graph. Right? You can read the period, but you can't read the frequency. You can read the amplitude. You cannot read the speed. You cannot read the wavelength. So these two only. A is the answer. What else do you think you can read here? Bro.
Wait, so you can only find the wavelengths when it's like displacement and distance, right? And the
Yeah lah,
distance
correct
is
lah. This
like...
one displacement time only period, right?
Wait, then how about frequency?
Frequency, you have to work it out. You can't read it from the graph. They're asking you
Oh.
what can be read off from the displacement time graph. You can't read out the frequency.
Oh.
Okay. Ah.
Yeah.
Anything else, guys?
Nope.
No? Okay, all the
Yeah.
best. All right, if you guys are trying to cram in the lenses, don't spend more than 45 minutes on the thing. All right, because it won't, like any longer than that, it won't be helpful already. And if you have spare time, just cram in another 1 or 2 more papers. Okay? Unless you are telling me that you don't have papers to do already. Do you all have papers to do?
Yeah.
Yeah?
Yeah.
Please continue to cram in all the papers, right, as much as you can, right? The only way to revise now is to cram in as many papers, right, to get as much exposure to the questions as possible. Okay, bye-bye, guys.
Okay, thank you.
Thank you.
Thank you.
Thank you.